Let's talk about hypothesis testing. Sections 3.6.4 through 3.6.6 in the book are what we're referencing here and can maybe help you understand this a little bit deeper. And my disclaimer for this video is to point out that if you take a statistics class, you'll likely dive quite a bit deeper into hypothesis testing and the different applications. And if we zoom out for this specific class, the reason we care about statistics is for us to be able to quantify our uncertainty related to our precision of any measurement that we're taking. And so we're going to take that a step further this time and say, what if we need to make some comparisons, or maybe we need to determine whether or not a statistical assumption has been made, hypothesis testing to help us verify statistical assumptions. Like if we have residuals between data and a statistical model that can't be distinguished from random noise, or maybe we want to determine if one mean sample mean is different than another sample mean, or maybe that the sample mean actually represents the population mean. So there's a lot of different ways that we can use hypothesis testing. So null hypothesis testing is a method for making decisions about a measured value, and those decisions are related to the population and not the sample, but we can use samples to make the determination. So that's pretty important for us to be able to do, since most of the time we're going to be taking samples from a population. And it stands for questions like this. Is the measured value within an acceptable range? So here are the steps. These are out of the book. You could follow along in the book, and it maybe gives you a little bit more information about each one of these steps. But you can see that the procedure itself is relatively straightforward. We're essentially defining a null and an alternate hypothesis, and we need to make sure that we're covering 100% of the cases through those. And so they need to be inclusive of all scenarios between the null and the alternate, and there can't be any overlap between the null and the alternate hypotheses. And then we're going to determine a confidence level. So how confident are we in the outcome that we're reviewing here? Then we're going to calculate an experimental value from the data, and we're using equations that we're familiar with to calculate this experimental value, and then essentially we're comparing that to a bound that we're setting based on the T or Z tables. And that's going to be determined by the number of samples. If we have greater than 30, then we're going to use the Z table. If we have less than 30, we're going to use the T table. And then we essentially just set that bound and see if our experimental value is inside or outside of that bound. And that tells us if we reject or do not reject the null hypothesis. And so it's pretty important to note, though, that rejecting the null hypothesis is a much stronger statement than failing to reject it, because we can show that the null hypothesis is not true, but we can't show that it is true. We don't have enough data to prove that it is true. And so by rejecting it, it's a stronger statement. Okay, so just comparing the two, this is maybe just helpful to think through. The null hypothesis that is shown is H sub naught or H sub 0. That essentially means nothing happened. There's no effect. There's no difference between the variables that we're comparing. Whereas the alternate hypothesis, something did happen. There was an effect, or there was a difference. And so when we're defining those, it makes it a little bit easier for us to see the outcomes if we define them in that way. So rather than talking through the theoretical and then using examples later, we're just going to step through an example right now. And as we're stepping through, you can see in the upper right-hand corner here, we have the steps that we're following for each one of these. So we've used this steam generator problem a few times, and we've got a sample mean of 4.008 megapascals and a sample standard deviation of 0.014 megapascals, 100 samples. And we're trying to figure out if we hit our target with the target pressure of 4 megapascals. So we're comparing our sample standard deviation, our sample mean with this target pressure. So we're saying this is the true value, or this is what we're targeting, or this is what the mean value should have been. And we're trying to compare that with our sample mean that we have. So can we make a statistically based determination with an associated confidence, of course. Without that confidence, it means nothing. but can we make a statistically based determination that we did or did not hit our target? So you can see this can be a pretty powerful tool if we're trying to figure out, is there too much noise in this sample or in this data set that we're looking at? Is there too much noise or too much spread? Is there too much precision uncertainty to be able to say if we hit the value or not? So this is a pretty helpful tool. All right, so now we have to determine what our two hypotheses will be, the null and the alternate. And so in this case, we're saying our null hypothesis is that our mean from our sample is actually the same as our mean for the population. So we're saying that mean for the population or the target value, you can say it in either way, that mean is 4 megapascals. So that's our target that we're trying to hit. So then our sample, the data that we pulled from there, given our sample standard deviation and our number of samples, is there too much spread? Can we actually determine whether or not we hit the target? That's what we're asking. So this makes our alternate. If we need to capture every possible scenario, that means if our null hypothesis is that it's 4, then our alternate is that it's not 4. So that's outside of those bounds. And so we need to make sure our mutually exclusive hypotheses, and we pick out a confidence, and we just pick out 99%. This is going to be pretty arbitrary. You can pick out 99, 95. There's going to be different justifications for picking different values, and that's going to be determined by you or your manager, or your engineering company, whatever it is. You are going to have to justify why you picked that. But in this case, we picked 99%. So using the equations that we're familiar with, we picked our z experimental value, which is our mean from the sample, minus our target point. So we've got 4.008 minus 4 divided by our sample standard deviation, 0.014 divided by our number of samples that is square rooted, and we end up with this 5.714. And so this is our experimental value. So now we're going to compare this to the table value. And essentially what this experimental is how far out from the sample mean might we expect the true mean to fall? So if we look up in our Z table with a 99% confidence, we find that the bounds are 2.575. And so because we set this equal to, we're going to have to look at the positive side and the negative side. So we have bounds on both sides. And essentially, if our experimental value is greater than this bound, then we can reject the null hypothesis, which is a strong statement. Whereas if it falls in between these 2 points, then we cannot reject the null hypothesis. So you can see that with a 99% confidence, we can reject the null hypothesis because our Z experimental is much greater than that 2.575. So essentially, our sample indicate that the target pressure of 4.0 megapascals was not accurately controlled based on a confidence level. And so we are saying we were not able to control that variable. Now we can continue to make this a stronger and stronger argument by increasing this level of confidence and moving this bound closer and closer to the point where we're very confident, and it's a very strong statement for us to say we reject the null hypothesis. This was not controlled up to a 99.9999, whatever that value is that gets us close to that Z experimental. You could do that if you needed to. Right now we can just say we reject the null hypothesis and we accept the alternate hypothesis that we set. And so if we go back to review those two, this is the null hypothesis is that it was 4, we reject that. That means we accept this, that it was not 4 megapascals. So this is a two-tailed test. That means we're looking at the tails on both sides and we are setting something equal to. So we've got our mean value is equal to this 4.00 megapascals. And so we have to look on both sides. But in some scenarios, we want to maybe look at a value that's less than or greater than, and so we have a left hand and a right hand tailed. So let's look at what those look like. So if our null hypothesis is equal to a value, that means we have to look at both sides of it. We have to look at the distribution on both sides. Whereas if we are greater than or equal to a set value, then we are looking at a left tailed And if we're looking at less than or equal to for our null hypothesis, we're looking at a right-tailed. So it's everything else is the same, but now our null and our alternate hypotheses are looking at the entirety of the left-hand or the right-hand side. So these are the steps that we step through. Again, it's very easy for us to step through these, but where I see students struggle is whether we're rejecting or accepting the different hypotheses. And sometimes it feels like we're almost doing a double negative. And so it's something that you need to practice a few times to get a real good feel for what that means to accept or reject the null hypothesis.